In this video, I'm going to talk about Kirchhoff's voltage and current laws. Kirchhoff's principles are based on the law of conservation of energy and the law of conservation of charges. First, we start with Kirchhoff's voltage law, which is based on the law of conservation of energy. If we look at this circuit, that as you can see, the resistors are one after another. So it means it's a series circuit. So I write it here, series circuit. We want to look at the Kirchhoff's voltage law in this circuit. So the battery is the source of energy or voltage. So it gives us voltage. And we know in resistors, energy is converted to different forms of energy. So we have voltage drop in resistors. Based on the law of conservation of energy, the energy can't be created or destroyed. So what does it mean? It means if I start from point, for example, A in here, it means a charge particle from point A starts moving around the loop or circuit, goes through the first resistor. If I name this one R1, goes through first resistor and then second resistor, and then moves through the battery and back to same point. According to the law of conservation of energy, energy of this charge particle at point A at the end of its journey should be equal to its energy in the beginning of its journey. What does it mean? It means we don't have any change of voltage. So it means delta V should be equal 0. Or I can say the sum of voltage in one loop should be equal 0. Sigma V equal 0. Let's try with this charge particle. So our charge particle starts from point A. Okay, moving here, we consider that wires have really low resistance, so we have no voltage drop. Going through R1, so R1 is a resistor, so it uses some of this energy and it's converted to different types of energy. So it means energy is used here, voltage is used here, or we have voltage drop. So we consider this one as negative. So I write negative V1. Then charge particle continues going through R2. Again, in R2 is resistor, so we have a voltage drop. Voltage drop, it means the amount of voltage decreases. So it should be negative again, minus V2. Charge particle continues all the way here. This is a battery. Battery gives voltage, gives energy. So it means the change of voltage is positive. So I put plus V battery. And the sum of all of these should be equal 0. As a result, we see V battery So what does it mean? It means when we talk about a series circuit, total V, that is V battery, is equal to the sum of voltage drop of every single resistor. So I write as a general rule for series circuit, V total equal V1 plus V2. And if we have even 10 resistors, we continue like this. This one is a parallel circuit. Again, I want to study Kirchhoff's voltage law for this parallel circuit. So I start again from point A, and this is our battery that gives us, let's say, voltage V. So we need to write Kirchhoff's voltage law for every single loop. So I start with loop 1, so I just try to show it with different colors. Okay, we start writing Kirchhoff's voltage law for loop number 1. And I say again, sigma V should be equal 0. Let's start. I start from point A again, a charged particle from point A, conventional current, start moving, going through wire and getting to, if I name this one R1, going through resistor 1. And because it's using energy, it's converting energy to different types of energy. So here we have a voltage drop. So I write minus V1. Then the charge particle continues. There is no other resistors in this loop. So it comes back to the battery and gains energy, gaining voltage. So it's positive. So plus V battery is equal 0. As a result, I can say V battery equal V1. Right now, I write the Kirchhoff's voltage law for my second loop. Second loop actually is this one. If I can show it, the green one, that if you can see this one. Okay, so I write again sigma V equals 0. And again, I look at from point A, a charged particle from point A, moving in loop number 2, going all the way here and going through R2, that is a resistor. So we have a voltage drop. So I write negative V2. And then after that, it goes through, there is no other resistors. So it goes through battery and it gains energy. So it means V battery then equals 0. As a result, V battery equal V2. So let's look at this one. So we see V battery, that is actually our V total is equal V1, and V battery or V total is equal V2. So because both of them are equal V battery, so it means V1 actually is equal V2. So as a result, for a parallel circuit, we write a rule, parallel circuit. For parallel circuit, we can say V total is equal V1 equal V2, and that's it. Okay. Right now, we look at some simulation from Phet. This is the battery, and I have resistor number 1 and resistor number 2 here. And I just changed this one to conventional current, so it's from positive terminal to negative terminal. Then we have a voltmeter here, and I want to measure the amount of voltage in different parts. This is 10 ohm resistor, and this one 10 ohm, and our battery is 9 volts. So I increase the voltage of battery to something that you usually have at school, a little bit more. I increase it to 20.5 volts. Okay. And right now I want to see what's the voltage here and see the Kirchhoff's voltage law. So I pick up a voltmeter and the voltage of our battery, and then I change this one. I want to measure the amount of voltage between the first resistor, this resistor, again, you see it's equal to V total. And again, I put it here. For the second resistor, sorry, I put it for the second resistor. And again, you see it's same number. So it shows when we have parallel resistors, the amount of voltage drop for each single resistor is equal to total voltage or V total. Right now, we look at a series circuit. As you can see here, I made a series circuit. So this is my first resistor, second resistor, and I show the conventional current again. So I want to see Kirchhoff's voltage law in this case. So again, I use a voltmeter. Firstly, just let me increase the voltage. Okay, 26.5 is okay. And then I want to measure the voltage in different parts of circuit. So firstly, I put it here, and you see it shows the voltage of battery, and you know it's positive. It should be positive. It's 26.50 volts. And then I measure the voltage drop across the first resistor. That is, if you can see, is 13.25. Okay. And then for the second resistor, as we know, it should be 26.5. That is our total voltage minus 13.25. So let's see if it's correct. And this one also is 13.25. It means total voltage is equal to voltage drop of first resistor plus voltage drop of second resistor. And if I increase the voltage of battery, for example, let's make it, for example, 43. Right now we have 43. Again, the sum of the voltage drop of these two resistors should be 43. Let's see. So this one is 21.5, and this one again 21.5. That if we add them is equal 43. That you see it agrees with the Kirchhoff's voltage law. Right now, I want to explain Kirchhoff's current law. Kirchhoff's current law is based on the law of conservation of charge. It means the total charge in a closed system is constant. It means if I consider junction, the total current into a junction is equal to the total current out of the junction. And if we consider the current in as positive and the current out as negative, it means sigma I equals 0. Let's look at one example. So sigma I equals 0 is Kirchhoff's current law. Let's look at our example, that is a series circuit with resistors 1 and 2. This is our I total. So I name it here I total going in resistor number 1, and thus I write it for resistor number 1, I total going in. So I put this one as positive, and then this I going through resistor 1, and I want to name this one I1. This is I going through resistor number 1, and because it's going out of this one, I put it as negative. I1 should be equal 0. As a result, I can say I total is equal I1. And then we continue this I1 going through R2, and I want to name this one I2. It means if for resistor number 2, I1 going in, so it's positive because it goes into resistor number 2 or this point, and I2 leaving that. So I put negative and then equal 0. And as Kirchhoff's current law, the total should be equal 0. As a result, I1 equal I2. So let's look at what's the conclusion. So I1 is equal I total. So I write I total equal I1, and I1 equal I2. It means I1 equal I2 equal I total, or in general, I can say for a series circuit, I total equal I1 equal I2 equal IN. Okay, let's look at a parallel circuit now. Right now I have a parallel circuit here with resistor R1 and R2. Again, I want to consider this junction and I name it junction A. And as you can see, I total going into junction A. And then I have here I2 that leaving junction A and I1 that leaving junction A. So I show the all current like this. So if I talk about junction A, we know sigma I should be equal 0. It means I in should be equal I out. I in is I total here. So I put it as positive, and as you can see, I1 and I2 leaving the junction. So I put minus I1 minus I2 equal 0. So as a result, I total actually is equal I1 plus I2. Or in general, I can say when I have a parallel circuit, I total always equal I1 plus I2 plus IN. Okay, this is Phet simulation. As you can see, I have a series circuit again here. I have 2 resistors and this is 1 ammeter. I want to measure the current in different parts of this circuit and to see if something that we got from Kirchhoff's current law for series circuit, it works here or not. Let's see. So here I put my ammeter to measure the total current. That is 2.15. Then I put it here in this junction. That is goes here 2.15. And then it goes through resistor number 1. And I want to put it here, the other side to see. Okay, 2.15. So it means the total current going through resistor number 1 and then, so I1 is equal total current. Right now the current going through resistor number 2, I want to see if it's equal. So current going in resistor number 2 is 2.15. Current going out 2.15. So we see I1 equal I2 equal I total. And also I can see, if I look at the resistor number 2, I going in 2.15, that is positive. So I going out also is 2.15, but definitely it should be negative. So the sum of them are equal 0. That is something that we expect from Kirchhoff's current law. The same thing's happening here. Current going through resistor number 1, 2.15, that is positive. Leaving is 2.15, that we consider that as negative. Again, the total is equal 0. Right now, let's look at a parallel circuit. Right now, I have a parallel circuit and I want to measure current in different parts. So firstly, I want to consider this junction here. And I want to measure the amount of current going in the junction. So the current going in the junction is 8.60. So the current in the junction should be equal to the current out of the junction if the Kirchhoff's current law is right. Let's see. So 8.60 going in, okay. 4.30 going out here, and 4.30 going out here. The sum of out is 8.60. So 8.60 in, 8.60 out, sigma I equals 0. Let's look at different junction. We go to the other side. For example, let's look at here, this junction. For this junction, you see this current going in, this one also going in. So I have this one in 4.30. That should be positive. And this one also going in 4.30. So it's 8.60 amps in and positive. And this one going out, that is equal again 8.60 amps. So the total current in is equal the total current out. So it shows the Kirchhoff's current law. Okay, let's see what we learned so far, and after that we go through finding R total for circuit. First, we look at series circuit that we learned using Kirchhoff's voltage law, that V total equal V1 plus V2 and plus any V that we have, and I total equal I1 equal I2. And when we talk about a parallel circuit, V total equal V1 equal V2, and then I total is the sum of I in all resistors. Let's look at series circuit first to find out about R total in a series circuit. So I start writing the formula again. I want to use this formula. So I rewrite it. And as Ohm's law, you know V equal IR. So I want to substitute IR for this. So I write it down. For V total, I write I total times R total equal, for V1 I write, sorry, not V, R1 I1 plus I2 Rn In. However, because it's a series circuit, we know I total equal I1 equal I2. And I want to say that, I write it here, so we know I total equal I1 equal I2 equal In, and I want to put it equal I. So I put I substitute I for I total and I1, I2, In. So I write I times R total then I rewrite it and I factorize I from here. So I write I R1 plus R2 plus Rn. If I simplify I with I, then I get the formula R total equal R1 plus R2 plus Rn for a series circuit. Right now, let's look at the parallel circuit. For parallel circuits, we have I total equal I1 plus I2 plus In. As a result, I can say I equal, if I use the Ohm's law again, Ohm's law formula, I see I equal V divided by R. So I write V total divided by R total equal V1 divided by R1. And as we can see, V total equal V1, V2, and we can say is equal V. So it means V total equal V1, V1 equal V2, Vn, and all of them are equal V. So I substitute V instead of for all are V here. So I write it down as V divided by RT Then I factorize V from here, so I write V 1 over I simplify V from this side to other side. So I get the formula 1 over RT. This is R total equal 1 over R1 plus 1 over R2 plus 1 over Rn. So this is the final formula for finding total resistance for a parallel circuit. Let's summarize. So as a result, we can see for series circuit, V total is equal the sum of voltage drop for all resistors, I total equal I1 equal I2 and IN, and R total again is the sum of all R's that we have. For parallel circuits, on the other hand, we have V total equal V1 equal V2 and equal Vn. I total is the sum of I's, and 1 over R total is equal 1 over R1 plus 1 over R2 plus 1 over Rn. I hope you found this video helpful. In my next video, we'll go through some problems for series and parallel circuit. Thank you for watching.